All right, so our next presenter comes from Petrobras, Dr. Luiz Monnerat. He's an HPC expert at Petrobras with over 30 years of experience with supercomputer design and seismic processing IT infrastructure. He's co-designed several top 500 supercomputers in the last decades, including Pégaso and Dragão, which are both among the top 100 most powerful systems in the world. In his presentation, he's going to discuss the motivation and evolution of the HPC infrastructure at Petrobras, which targets a mix of commercial and proprietary applications, mainly for geophysics, research, and reservoir engineering. Dr. Monnerat, welcome. You're currently on mute.
Hi, Brian. Thank you very much. Welcome. Well, I'm very pleased to be here to present our work at Petrobras, and I would like to thank you and the HPC Advisory Council and Stanford for the opportunity to be here, and also to all the audience for their attention. Thank you very much. And well, I will try to follow this very simple agenda. And are you seeing the presentation? Sorry. Yeah. Okay.
Sorry. Yes, absolutely.
Yes. And so I will start talking about why we use HPC at Petrobras, and well, sorry. And then talk about how HPC evolved there. And then I will talk about how we are now, including the use of cloud, and then conclude this presentation, okay? And well, and the reasons that we use, sorry, it seems to be, let me see here. Sorry about that, okay? And let's start again. And the reasons that you use, sorry, it seems to be, okay, let's go. And the reasons why use HPC at Petrobras are much related to our business, and so they are not much different from other energy companies, because most of our capacity, in fact, more than 90% of our capacity, is dedicated to seismic processing and reservoir simulation. Okay, and I understand, although in fact we have another important demands such as petrophysics and geomechanics and so on, but more than 90% of our capacity is dedicated to seismic and reservoir. And I understand that some of you should not know well about seismic processing and reservoir simulation, so let's try to explain it a little better. Well, let's first talk about seismic, which aims to create images of the Earth's subsurface in areas of interest for oil and gas exploration and production, like this one that you see in the left. And these images are very important information for any energy company for several reasons. First, these images allow us to see and understand the subsurface and then look for oil and gas in a way that's seismic processing is really essential for us to find oil and gas, of course, and also these images are essential for us to position the oil wells that will be used to extract the oil and gas that we have found. So they are really very important for our business. But please note that it doesn't mean that supercomputers find oil by themselves, or even that they are able to create the images of the subsurface by themselves. In fact, our supercomputers are indeed very powerful tools that are used by our technicians to generate better images and better reservoir simulations, so improving the quality of the information we need for very critical decisions for our business. And reservoir simulation solves a quite different but very related scientific problem, as its main goal is to simulate the behavior of the oil and gas and water inside each reservoir during its lifetime that may span for decades. And based on these simulations and with the help of the seismic images and other information, we decide how many oil wells we should drill in each reservoir and their locations and other important decisions. So in fact, both seismic processing and reservoir simulation provide us with information to drill our wells and produce oil and gas. And so one may conclude that our HPC goals are much related to the oil wells that we have now and that we will do in the future. And it's really quite true. It's quite true. But in fact, the oil wells are not the only reason. But even if they were the only reason, they are a quite relevant reason for us to have HPC, okay? Because each deep water well, typically costs more than $50 million, and Petrobras will drill more than 300 offshore wells in the next 5 years, okay? Even though some of those wells may cost less than $50 million, all those 300 wells may cost around $10 billion or even more. Okay, so they are quite important reason for us or any other energy company to have HPC. Okay, and as I said, in fact, there are other reasons beside that, but anyway, that's a very important reason. And well, before going forward to the next topic in the agenda, let's now know a little better about our seismic and reservoir HPC workloads, which will allow us to explain why we have very different supercomputers for reservoir seismic. Let's start with seismic, and I may say that more than 80%, maybe 90% of our capacity is dedicated to seismic, which doesn't mean that seismic is more important than reservoir or other demands, but it really means that the seismic applications are much more compute intensive. Another point is that the seismic applications use single precision, which means 32-bit floating point operations, and we have very big data sets. And for seismic, we run several different applications, and at least 80% of our processing capacity is based on GPUs, but we have a mix of small and big jobs with CPU jobs and GPU jobs, and each big GPU job may use more than 1,000 GPUs. And almost our GPU capacity is dedicated to in-house applications, basically because the most critical seismic applications are not available commercially, and they are developed in-house, and they typically are the most compute-intensive applications. And as we started developing for GPUs quite early in 2008, our seismic coding compute-intensive applications basically use GPUs. Well, now let's talk about our reservoir workloads, which are really quite different. Of course, there are exceptions, but in contrast to seismic, reservoir typically uses commercial applications and double precision and much smaller data sets. And we basically don't use GPUs for reservoir. Besides, in each reservoir job, we typically run a shared memory application with no internode communication, but we commonly have several hundreds of those reservoir jobs running at the same time. And so we must have quite different machines for reservoir and seismic, not only because the GPU and CPU use. And in fact, even for seismic, we should have a number of different machines as we have a number of quite different seismic workloads. And while I told about just seismic reservoir, please be aware that we have other HPC domains that are critical for our business, such as petrophysics and geomechanics and machine learning, of course. And so we may even have another clusters for other demands. Well, we also have our capacity split in two different data centers. One is proprietary and the other is rented. The rented data center is virtually dedicated to HPC, while in the proprietary one, we have some other relevant workloads. Well, although both are in the city of Rio, they are not so much close each to other. As they reside in opposite sides of the town. The proprietary data center resides in an island in the Guanabara Bay here, and the other data center is about 20 miles away in the other side of the town, okay? And, well, in this picture, I show the location of the proprietary data center. It resides in an island. In fact, this island in this island, we have one big university and several research centers from other companies. This picture is shows our research center, and here is in this white box here, we have the data center, okay? And basically, my desk is near this window here, okay? Well, let's see how HPC evolved at Petrobras. In this picture, well, it's a nice, you can imagine as HPC is so critical for our business, it should not be a surprise that we have HPC for quite a while. That's a picture from 1969. Of course, at that time, terms like HPC and supercomputers didn't exist yet, but this IBM 360 was our first computer for geoscience. And our scientific processing capacity was based on IBM mainframes for decades, and I personally worked with the IBM mainframes, not this one. I started to work at Petrobras in 1987, but with IBM mainframes for seismic. And as many other companies, we started with risky machines in the 90s, basically with SGI Power Challenges and IBM SP2. And I also worked with Power Challenges and SP2s, but in 1997, I was in charge, along a few other colleagues and one Brazilian university, to build our first x86 machine. I don't have a picture of this first x86 machine, but I have a picture of the second one that was built in 1999. You can imagine that it was a quite cheap machine, but in fact, it was able to produce a good amount of seismic at the time. And so, in fact, we started quite early with x86, but in 2007, exactly 10 years after our first Linux machine, we started a project to study new compute solutions. At that time, we studied a few options, including FPGA, but the main options were the cell processors, which could be found in PlayStation 3 consoles, and the GPUs. We first built this small PS3 cluster in 2007, and we ported one of our own seismic applications to it. And later on, we also ported the same scientific seismic code to a GeForce GPU. So we run an important seismic application in both the GPUs and the PlayStation cluster to compare. And these results are public in a number of papers, but anyway, you can imagine that the GPUs won this contest, and we were able to have our first GPU cluster by the end of 2008. This was our Griffo 1, which provided us with basically 1,000% gains in terms of cost, performance, and power consumption. And at that time, we didn't have any commercial application for GPUs, and so we have been developing code for GPUs for almost 15 years. Even AWS and Azure took a while, a long time, to have GPU instances available, and they did it only in 2016, 8 years later. And even though the Grifo 1 was extremely good for seismic, it was not ranked in the top 500 because the NVIDIA GPUs at that time, they were very good for seismic, but they didn't have good double precision performance. And so they were not good for LINPACK. In fact, this was, this was not a problem for us because we don't target LINPACK, and so we didn't care, as our seismic applications don't need double precision, and our goal was not the top 500. Well, but please note that we find that to be in the top 500 is nice, but it's not our goal. Okay, I do believe that the top 500 is important and relevant, but we really don't design our machines for LINPACK, and we have never done it. Okay. Then after the Grifo 1, we had the Grifo 2 and 3, both bigger than Grifo 1, but they didn't appear in the top 500 for the same reason. But the third generation of the NVIDIA GPUs with the Maxwell architecture did have both single and double precision performance. So these GPUs were good for seismic and also good for LINPACK. Then when we built our Grifo 4, this machine was extremely good for seismic and was also able to be ranked in the top 500 as the biggest supercomputer in the energy industry. And please note that we are aware that some companies don't rank their systems in the top 500, top 500. So there could be systems bigger than the Grifo 4 in the energy industry at that time, but we are simply not aware of anyone bigger. And it was quite a landmark for us. We had already had some machines in the top 500 before, but not in such a good position. But a few years later, we had a big price. The oil price dropped a lot in 2014, and for sure it was not the only problem Petrobras had at that time. We had lots of problems in a way that we were not able to invest in HPC for years. And so, due to the lack of investments, we arrived at 2018 with our HPC infrastructure quite obsolete. Then in 2018, we built a plan to revamp our HPC infrastructure, but we didn't have the resources, budgets, and also the data center to completely revamp it in just one movement. So we had to do it in waves, which led to some fragmentation, which means that we now have more than 10 different clusters. It's not a big issue. It makes things more complex, a lot more complex, especially, but in fact, we would have some fragmentation anyway, as clusters that are good for reservoir are not good for seismic. We have two different data centers, and even inside seismic, we have quite different workloads that require different machines, okay? But anyway, it made things much more complex. So let's see our current HPC infrastructure. That's quite good for our business, but as I said, we have more than 10 different clusters, while we could have maybe 6 or 7. As I said, we should have anyway different clusters for reservoir, for seismic, different clusters for each data center, and also inside the seismic, we would need different clusters. Well, for example, for reservoir, we have now 3 different clusters in production, Guaricema, Libra, and Búzios, but all their nodes are quite similar with 40 cores and the same amount of RAM, and of course, the same operating systems. So we basically manage all those reservoir nodes as a single virtual cluster with a total of 1,200 nodes. And of course, it's much more difficult to install 3 different clusters than a single one. But we really didn't have a choice. And for seismic, we have also a number of different clusters in a much more complex environment. Let's see just the biggest ones, which are Phoenix, Atlas, Dragão, and Pégaso, the newest one. Okay. And as each one was built in a different year, and as we had, as a result, having the biggest supercomputer in Latin America for 4 years in a row, and also the best Latin American supercomputer in the Green 500 for the last 4 years. And so let's have a closer look into Pégaso. It has more than 2,000 GPUs and it's ranked as 33 in the top 500. If we put all those rows in a single line, it would be 35 meters long, including the Lustre file systems. We have more than about 20 petabytes in Lustre file systems. And I have a nice short movie about Pégaso. Let me show it here. I hope you will enjoy it, even though, sorry, the subtitles are in Portuguese. You see, you have, basically we have 5 rows. One is smaller than the others. The big rows, the 4 big rows have 14 racks. And you see that the rows are quite long, not so long as many other machines. You see that Pégaso is 33 in the world. We have 32 bigger machines than Pégaso. And well, that's it. Oh, sorry, let's go forward. Yeah, well, and well, let's see this graph. After implement all those clusters, this graph shows the evolution of our capacity since 2018. Well, I know, and everybody knows that flops is quite far from a perfect comparison unit, but it's the one that we have. Another point of confusion is that, well, we have been using FP64 flops to show our evolution for quite a long time, and while FP64 flops used to be the same as the top 500 R peak until basically 2021. Since the 800 GPU is not true anymore, but we still use FP64 as a comparison. And also, please note that in this graph, we plot the sum of the capacity of all our clusters, including those that are not in the top 500. But in fact, what this graph shows is that we had about 3 FP64 petaflops in 2018, which was quite bad for our business. And 1 year later, we were 3 times bigger. And 3 years later, by the end of 2001, we were more than 10 times bigger, okay? And in 2022, we got a good deal of new capacity, especially with Pégaso. And, well, this other graph shows the oil and gas petaflops in the top 500, and this one is in our peak. We should look at it with care, especially because some companies do prefer not to be listed in the top 500. But anyway, it shows that the energy companies have been investing a lot in on-premise capacity for HPC. And it's interesting to note that, well, according to the top 500, we did have no HPC addiction in in 2017 and again in 2022. Well, it may be related to the sharp drops we had in the oil price in 2016, 2020, as you can see here. It could have been reflected in this graph, in this number. But the cloud is also playing a role, and let's talk a bit about cloud. Well, I believe that everybody knows that the cloud brings important opportunities, but it's also quite expensive if you use it without care. So let's use it with care. And that's what we are trying to do in a way that in our plans, the cloud will be very important for our HPC. One big problem is that porting seismic to the cloud is quite complex and may take several years, but it's much more, let's say, simple for reservoir and machine learning. So what we are doing is to work a mixed environment for reservoir and machine learning, while for seismic, we should first use the cloud for application development. Well, I don't know if I have much time left, but let's draw a few simple conclusions. First, that HPC is really important for our business, and we started with it a long time ago. And along this way, we played with several different architectures, and we have been using GPUs since 2008 and Linux since 1997. We recently had a lot of investment in HPC, which allowed us to expand our HPC capacity by 20x since 2018. There has been a lot of work. And as I said, there are lots of, at least 32 machines much bigger than the Pégaso. But installing a big machine is quite an issue. Everybody knows that's not easy, but installing more than 10 is quite difficult. It has been a lot of work, and our team has been doing a very good job with it. And we are using cloud, but not very much yet, but it will be very important for us. Well, I think that's it. I would like to thank everybody for the attention, and also to Stanford and the HPC Advisory Council again. And thank you. I'm here, glad to take any questions that you might have. Thank you.
Thank you, Dr. Monnerat. Great presentation. I remember seeing a PlayStation 3 cluster at ISC. I think it was 2007 timeframe. So every time I see a picture of something like that, it always brings back those memories. Yeah, that IBM cell processor was really interesting, and how people were starting to try to take advantage of that. One question came in. Oh, I got more coming into. I'm assuming that when referring to FP64, you mean float 64. I understood
Yes.
that for reservoir simulations, you're using at flotation point computations. How do you handle the intensive FP64 computations using GPUs, especially in the early days? Did you do fixed point to floating point conversion?
No, in fact, for seismic, we use single precision floating point, which means FP32, okay? And the GPUs were always good for FP32, as they were originally designed for visualizations for the gamers, and so they worked very well for seismic. But for reservoir, in fact, we may have a problem with propagation of errors. So a small, you run simulations that try to simulate, sorry, for example, 20 years of oil production. So a small error here can turn to be a big error in 20 years. So FP64 is important for reservoir simulations and for other reasons. For the applications that we had at that time, about 10 years ago, in seismic, propagation of errors, what not a problem. They may be a somewhat bigger problem nowadays. And so FP32 was always good for seismic, and it is still good. But for reservoir, since a long time ago, we always used the floating point 64-bit, and we still use, and I believe that everybody uses. In fact, the most, not only Petrobras, but most of the energy companies, I do believe that use commercial applications for reservoir simulation, and basically all of them use FP64. For a long time, we didn't have any commercial application for reservoir simulation using GPUs. From maybe 3 to 4 years ago, we do have some offers using GPUs for reservoir simulation. I don't believe it's only related to FP64. It may be related to the interprocess communications as well, and to the complex of the application.
Thank you. And one last question here. Petrobras just announced the new cluster Gaia. Can you tell us anything about it?
Yes, we, in fact, Gaia has been physically installed, or it's almost physical installed, and we will start to install softwares and things like that. And it's dedicated for research, okay? And basic research in seismic. And even the other cluster that I've been showing here, like Guaricema and Atlas and Dragão, and all the others are for production, for seismic production, and also for reservoir production. And Gaia is a new one. It's not in production right now, and it is going to be dedicated for research.
Fantastic. Well, congratulations. We look forward to hearing more.
Okay, thank you very much.